What if you could send 2 bits of information by physically transmitting only one? Welcome to this explainer. Today, we're not just tearing down the theoretical foundations of quantum mechanics. We're actually going to build up the code to make that impossible paradox a reality using Qiskit. Okay, let's dive into this. To really grasp how we pull this off, just think about this paradox for a second. You want to send 2 classical bits of information, like a 0 and a 1, but you can only physically transmit 1 single bit across a cable to do it. Now, in classical physics, there's just no way. That's a hard impossibility. But in the quantum realm, this is a very real protocol called superdense coding, and it's exactly what we're going to deconstruct today.
But to get there, we hit an immediate hurdle. How do you even write down a state that's both 0 and 1 at the exact same time? I mean, if we're going to manipulate these fluid superimposed states, we need a completely new alphabet. We have to be able to describe this mathematically before we can even think about programming it.
So, first up are tools. You're going to need Qiskit and a local environment. But listen, be warned right now. The absolute biggest trap you're going to face here is a kernel mismatch. If Qiskit imports perfectly in your terminal, but your Jupyter notebook suddenly throws a module not found error, you are operating in 2 completely different Python environments. Just make sure you select the exact Python kernel where you ran your pip install. That one little fix will literally save you hours of frustration.
Now, once you run your first circuit, let's say you're putting a qubit into a superposition with a Hadamard gate. How do you actually know it worked? Well, we're expecting roughly a 50-50 split. Out of 1,000 shots on your local simulator, you should see something like 450 to 550 for your counts. If you see something wildly skewed, like 950 to 50, that's not some weird quantum anomaly. That's your signal something is off with your code, like maybe you measured before applying the gate. Oh, and always check your state vector. The amplitude squared must sum exactly to 1. That is your ultimate sanity check.
All right, let's look at this new alphabet and see how it builds our conceptual framework. Welcome to Bra-ket notation. Notice how a ket, that's the straight line in the right angle bracket, is a column vector representing your quantum state. A bra, the left angle bracket and straight line, is its exact mirror. It's the conjugate transpose. It becomes a row vector with complex conjugated entries. The notation here is beautiful because it perfectly mirrors the vector math underneath it.
Now, what's really fascinating is what happens when we crash these 2 pieces together. If you multiply a bra and a ket, and the inner product, they collapse into a single complex number. And that number tells us the overlap, or the relationship between 2 states. But if you flip them around and do an outer product, a ket followed by a bra, you don't get a number. You get a matrix. You've literally just built an operator. So inner products give us measurement probabilities, while outer products let us build the machinery that actually transforms our states.
If that algebra is feeling a bit dense, let's translate that Bra-ket math directly into geometry with the Bloch sphere. Instead of tracking column vectors, just picture a globe. The north pole is our state 0. The south pole is state 1. The polar angle, how far down you pull from the north pole, that controls the mixture of 0 and 1. But quantum mechanics has this whole other dimension, the relative phase. That's tracked by the azimuthal angle, kind of like longitude around the equator. And that entire equator, it holds equal 50-50 superpositions, just with different phases. So, with our alphabet and our geometry in place, we're bound by a few rules. The postulates of quantum mechanics govern basically everything we do. Postulate 1 tells us our state is always a unit vector. Postulate 2 says that as long as our system is closed, it evolves smoothly and deterministically via a unitary operator. Think of it as basically rotating our point around that Bloch sphere. And then postulate 4 lets us scale up. To describe multiple qubits together, we just use a tensor product to combine their individual spaces.
But here is the crucial point. Postulate 3, measurement. Let's slow down here because this is where that smooth deterministic rotation abruptly stops. The probability of getting a specific outcome is the absolute square of the inner product between the state you are in and the state you're measuring for. And the very moment you measure, that fluid superposition, it's gone. The state snaps. It collapses irreversibly to that measured value. Make sure you've got this down because this is the load-bearing math for literally everything we'll do moving forward.
Understanding that intense fragility of quantum states leads us directly to a hard, unbreakable limit in our universe, the No-Cloning Theorem. You cannot copy an unknown quantum state, period. There is no quantum copy and paste.
I'm leading with the result here because this impossibility is actually profoundly useful. It's exactly why quantum cryptography works. If an eavesdropper intercepts a transmission, they fundamentally cannot copy it to read later without destroying the original and instantly alerting the sender.
Now, this proof trips people up the first time they see it, so let's go slow. Let's just assume a hypothetical copying machine, a unitary operator U, can copy two different arbitrary states. Because it's unitary, it has to preserve inner products. But when you run the math, you hit a stark contradiction in step 3. The inner product of the two states must equal the square of the inner product. Well, what kind of number equals its own square? Only 0 or 1. This mathematical wall means you can only ever clone identical states or perfectly orthogonal states. You can never ever clone an arbitrary unknown state. And this brings us right back around, brilliantly illustrating why our opening paradox is possible. Let's return to superdense coding. Now, before we look at the matrix math, let's just trace the shape of the protocol. Alice and Bob want to communicate. First, they share an entangled thread, a bell pair of 2 qubits. Alice takes her 1 qubit, applies a specific gate to it, and physically sends only her 1 single qubit over to Bob. Bob then takes the qubit he just received, pairs it with the half of the entangled pair he's been holding this whole time, and measures them together. So how does sending 1 qubit transmit 2 bits? Well, here's the mapping matrix. Because their qubits were entangled, whatever Alice does to her 1 qubit transforms the entire shared state. If she wants to send 0, 0, she does nothing. She applies the identity gate. For 0, 1, she applies an X gate. For 1, 0, a Z 8. And for 1, 1, both. By manipulating just her half of the system, she steers the joint reality into one of 4 distinct orthogonal Bell states. Bob's measurement then perfectly distinguishes which of the 4 realities she chose. It's wild, right? The sheer depth of what we've covered today requires a very specific kind of study habit. I mean, I could give you a finished cheat sheet, but just copying someone else's notes is a weak way to learn. Notice the deliberate blank spaces we've left here. They're the things doing the real work. If you're preparing for an exam, build this matrix yourself. Fill in the postulates, the Bloch sphere angles, the no-cloning proof. If you hit a blank spot you can't fill, that gap is exactly the spot you need to rewatch. Compressing the material yourself is what actually cements it in your brain. So, we've built the alphabet, we've explored the sphere, and we've broken classical limits. But I want to leave you with a lingering, kind of mind-bending question. In our superdense protocol, Alice sends 2 classical bits of data by physically handing over just 1 quantum bit. But we know a single qubit can't possibly hold that much information locally. So, if the moving qubit doesn't contain the 2 bits, where exactly does the data live while it's in transit? The answer lies in the reality of joint correlations, entirely separate from local space. And exploring that, well, that is where the true depth of quantum mechanics begins. Thanks for learning with this explainer today. Keep building and keep questioning.